Hi, my name is Huang, and in this session, Daniel and I are going to be talking about bringing capabilities of PyTorch to new programming languages. I'll start off and say a little bit about what is it about PyTorch that enables us to build these frameworks in other languages. Then Daniel will introduce Torch for R, and finally, I'll talk about Hasktorch, a Torch library for the Haskell programming language. There are certain design and implementation aspects of PyTorch, going back to the 1.0 release, that really enabled a lot of this work to happen. So the first is that in PyTorch 1.0, the C++ backends of PyTorch were consolidated into the libtorch library. Now, libtorch is a machine learning library for C++ in its own right, with tensor operations, neural network functions, GPU support, automatic differentiation, and so on. And it also serves as a technology base for a lot of the productionization and deployment capabilities of PyTorch that are being built out. Having libtorch also means that any other programming language that's able to bind C++ through a foreign function interface is able to import all those capabilities wholesale. And here you see examples of libraries and programming languages that have taken advantage of that. The next aspect I'll mention is that libtorch has a specification. It has metadata that describes every single function and every parameter of every function. And what that allows is a single developer can consume that specification and using code generation, automatically produce raw bindings to the entirety of the libtorch library. And with little manual effort, almost overnight, you have thousands of functions that are now available in your programming language. But the implementation doesn't end right there. On top of these raw bindings, we create higher level interfaces to make the library feel like a native R or Haskell or whatever programming language that makes it feel like a native library in the programming language you're working in and takes full advantage of the strengths of your programming language. And we'll see some examples of that later in this talk. The last thing I'll mention also comes from this push for productionization, and that is this shift that also occurred with PyTorch 1.0 of thinking about models as just being Python code to thinking about models as being data. And specifically, I'm talking about serialized representations of models such as ONNX and torch script. And these serialized representations of models, again, were motivated by the deployment of models, but they also serve to separate out your representation of model from the particulars of the Python language runtime. And what that means is you can take a PyTorch trained model and go through a serialized representation of the model and then bring that into R Haskell for fine tuning, or vice versa. Take a model that's trained in Haskell R and then piggyback on the deployment patterns that are there for PyTorch. And ultimately, what that allows is to not be tied to any one particular language runtime, just because that's where all the valuable, expensive to train pre-trained models are. We can kickstart an ecosystem of models that crosses the boundaries of programming languages. So I've said a little bit about PyTorch and how it's enabled working across different programming languages. I'll introduce Daniel to talk about Torch for R.
Thanks, Austin. My name is Daniel, and I am a software engineer at RStudio. Today, I'm going to talk about Torch for R. We are happy to announce the first release of Torch. Torch is an open-source R package implemented on top of libtorch. Most of Torch's code is auto-generated from libtorch's declarations, but we also provide neural networks abstractions implemented directly in R. Torch's API is very similar to PyTorch's, but looks familiar to our developers. For example, this is how we define a simple neural network in Torch. We use the NN-model function to create a model, and we pass the initialize function implementing what are the model weights and how they are initialized. We then pass the forward method that defines how the model weights are used in this model. On top of Torch, we have also implemented many of the most commonly used models, like convolutional and recurrent layers, and many different activation and loss functions. Implementations of optimizers, datasets, and data loaders are also provided in the Torch library. Building on top of libtorch allows us to make it deeply integrated with R. For example, the AutoGrad system is completely extensible using pure R code. This example shows how you can create an AutoGrad function that can be used as any other tensor operation, also taking benefit of automatic differentiation. This is useful if you have an operation that is not composable of other tensor operations, or that its gradient computation would be faster if you knew that the operation would be fused. You only need to define the forward and a backward function returning the gradients for each input to forward. The R language has a strong community of researchers across many different fields. See, for example, the R OpenSci project. They act in fields like economics, genetics, psychometrics, bioinformatics, with the Bioconductor project, and many others. Deep learning and PyTorch have already proven its success in fields like computer vision, natural language processing, speech recognition, and others. We believe that researchers in the R community will use Torch to find entirely new applications for it and push the frontiers of what's possible. Torch for R is still in early development, and we still have a lot of future work. First, it would be great to have better interop with PyTorch. For example, we could make 0 copies when transferring Torch tensors to PyTorch and vice versa. Next, we need to build a larger ecosystem with problem-specific packages like Torch Audio, Torch Text, and Torch Probability. We will also implement features to make Torch for R work with larger datasets, like parallel data loading and multi-GPU libraries. That's it. Thanks very much. You can learn more about the Torch for R project in torch.mlverse.org, and no matter what are your skills, it's possible to contribute to Torch development. Feel free to reach out on GitHub or email.
Thanks, Daniel. I'm going to introduce Hasktorch. Hasktorch is the result of work by a great team of collaborators on the core team as well as contributors from the open source community. It brings Torch to the Haskell programming language. Now, Haskell is used quite a bit for programming language research and also in industry, but might not be as well known in the machine learning world. So let me briefly introduce it. Haskell is about typed, pure functional programming. In functional programming, your programs are built up by composition of mathematical functions. This is identical to how neural network architectures are built up by composition of layers, where the layers themselves are mathematical functions. In some sense, the neural networks are a form of differentiable functional programming. This isn't my idea. This has been articulated over the years by people like Chris Olah and others. This also extends to how neural network computations are implemented in Hasktorch. You use the composition operators and higher order functions that are built into Haskell. This reflects how functional programming and neural networks are a natural fit for each other. In Haskell, you also use the type system to express the properties and invariants in your program. This is done in a lightweight way without much boilerplate, in contrast to some statically typed languages that are boilerplate heavy and sometimes make your code a bit rigid. Haskell is able to do this by bringing in ideas and features from programming language research, such as type inference, some dependent types, and generics, which automate away boilerplate and also leave your program flexible in ways that matter. In fact, one of the things Haskell is most known for is the ease with which you can refactor large, complex code bases. So by bringing Torch to Haskell, we now have a playground to explore this intersection of machine learning, type functional programming, and programming language research. You see an example, a snippet from Chiara's work that's going to be presented at the NeurIPS 2020 workshop on program synthesis using Hasktorch. And here you see also an example from Torsten's live demo for the Berlin Functional Programming Group, showing how by providing type information about your model, an IDE such as VS Code can provide you suggestions as to what to implement next, just based on the holes of the types that you've specified. Torsten takes us a step further in some of his work on compiler check type neural networks. Neural networks and their components have data inputs and data outputs at the beginning and end of the neural network, as well as in the modules that comprise the neural network. You'd like your type system to be able to validate these data and make sure all the shapes and of the data are consistent. Now, at first glance, that seems difficult. On one hand, I don't want to hard code all of my tensor shapes as in inputs and outputs. I wouldn't be able to use that code, reuse it, if I say change the data set. At the same time, if all I do is say that my neural network and each of the layers just has the generic sort of tensor type as inputs and outputs, I'm not providing the type system much information to go on to check for correctness. One solution that Haskell provides to this is the availability of type-level functions. With type-level functions, the output type is a function of the types of your input. And in this way, you can encode the invariant, such as here, the shape of the output of convolution operation, without rigidly sticking to a fixed type. Now, this calculation may look familiar for those familiar with convolution operations. The difference is this doesn't happen when your program runs. This calculation doesn't happen. It's not a check that happens when your program runs. It's a calculation that happens when you compile your program and the output type is computed from the input types. And this, again, gets you a bit of the best of both worlds. So you get the flexibility of being able to reuse code if your data changes. At the same time, your compiler is able to provide you with a guarantee that you won't have a single dimension error when you run your program. So I provided a glimpse into some of the interesting directions that we're exploring with Hasktorch. If this seems interesting to you, whether you're coming from a machine learning background, you're interested in functional programming, or you're coming from a functional programming background and would like to contribute, don't hesitate to join us on Slack. You can contact hasktorch@gmail.com for an invite. Visit our GitHub or visit hasktorch.org to get started. I'd like to end with this quote from this article on machine learning frameworks brought up in last year's PyTorch conference. And it brings up this idea that our tools of frameworks and programming languages are more than just tools that enable our research. They also guide us into thinking about certain directions of solutions, certain directions for research, certain directions for applications. And it's the hope of both Daniel and myself in implementing these frameworks and bringing PyTorch to other programming languages with their own strengths, their own ecosystems, and entirely new communities that will perhaps open doors to exploration of research and applications that would otherwise be left unexplored. And with that, I'd like to thank you for your time. Do check out Torch4R, check out Hasktorch, get in touch, and let us know what you think. Thank you.